myself in it.
Okay, thank you very much, people. Everybody knows me here, so I'm Pablo, and I would like to talk about my PhD progress so far during these 3 years. And the topic of my thesis is measurement and prediction of nonlinear acoustic liners in the presence of high-level multiple tones and grazing flow. A big name and several things, but we want to focus primarily on the multiple tone thing, on the single degree of freedom liners. So basically our motivation here is to study the aircraft noise. And we have this problem that near the airports we have this community issue related to noise, and we have been seeing the increase of the number of aircrafts flying all over, and then it's becoming more affordable, but at the same time we are increasing the sound pressure level near the airports. So the industry have this challenge to certify aircrafts that has lower noise, and that's what we have been working on. And basically there are several sources of noise, and we are looking more at the fan noise, and this is a very difficult type of noise to model, and it's a buzzsaw noise composed by several tones. And then we have, let's say in this region here of the nacelle, the application of these lining materials. So basically these lining materials are exposed to very high sound pressure levels, grazing flow incidence that goes through it, and there's this interaction between the multiple tones of the buzzsaw noise. And we want to model, because all the models available nowadays in the literature talk about the model just frequency by frequency, considering that the problem is one tone at a time. We see that if we have the blade passage frequency, the level of this tone is much higher than the others. So we consider that we can model one frequency at a time. But we have been seeing that the impedance of this material, which is the ratio of the acoustic pressure and the acoustic velocity, is not the same for single tone and a multiple tone instance of this sound. So basically these are the origin of these materials. I divided here in 3 years of the PhD just to have an overview. The first year we studied the literature review, how the analytical models are presented. We did some measurements using a portable impedance meter, so it's a normal instance measurements, and we studied and proposed another semi-empirical model based on these literature review models. On the second year I traveled to Brazil to do some measurements in a facility that we built there using grazing flow facility. So we have not only the sound impinging on the liner, but a grazing flow too. And then there are several impedance reduction techniques, which are experimental techniques we use to measure the impedance of the liner using microphones away from the sample or on the opposite side of the tube that we are analyzing there. And on the third year we are focused now on the numerical models and how to visualize the sound through the holes of these materials, and we are using multiphysical models. So basically, if we think a liner in a very simple way, we have a Helmholtz resonator, which is composed by a cavity which has a volume, and this neck, which can be, let's say, think as a perforated plate with several holes, and the cavity below, it's composed by this array of several honeycomb structures and a backing plate on the back. And if we model it as a simple 1 degree of freedom system, we have this mass and spring model, which is we can model as a like a EDO, how they call the differential equation, like an ordinary differential equation. And there are three main models we study in this work. Two of them are time domain models, presented in 1971 and 1984. And this model is a frequency domain model. But we are trying to develop a time domain model to study this interdependence, or let's say the combination of these tones, multiple tone response. And then we propose this model here, which basically, if we see it's a mass here, so acceleration of a mass, this component here is the dissipation, provided that if we think another component here is a damping of the system, basically we can see that the dissipation mechanism is composed by the boundary layer formed here, say the shear stress caused in this region of the neck. And at higher sound pressure levels, we see the vortex rings, and there's another mechanism here. We include this velocity component, and we are trying to model this velocity in a way that we can join the pure tone excitation, multiple tone excitation, and try to figure out how it works. So let's see the liner geometry. We extracted one piece of this material, and then we cut one part to put in a sample holder. So basically this sample holder, we reproduce the same sample using 3D printing techniques and vary the geometry of these samples. So basically we vary the hole diameter, the thickness of this perforated plate, if we think it's a perforated plate, the size of this the liner, let's say the cavity depth, and then we can evaluate to the porosity of this material. So if we change the number of holes and so on, we can have different porosities. And basically we analyze these samples in a microscope and see the main, let's say, deviations we got using this manufacturing process to study, let's say, parametrical analysis of the geometry features of this material. And then we put this sample in the end of a tube. This is the portable impedance meter, and we did two measurements, different measurements. This one is a flanged, let's say, measurement directly on the sample. And the second one here is using this sample holder. I'll show you this cutted piece. So basically these two techniques, let's say, have some constraints here. So if we analyze this flanged configuration, the porosity seen by the diameter of this tube is different from the, let's say, the area on the backing plate here. So basically we see that in this region here we have a mismatch of areas of the porosity. So we need to deal with this, and this causes some uncertainties and lower frequencies of the measurements. And this is a standard tube used in the ISO and ASTM standard. So we think another way to instrument this sample using another technique, which is an in situ technique. We got these very tiny microphones that have 1.6 millimeter diameter, and we created this. We have a back plate, let's say. We made a hole and then insert this microphone, and then we glue the sample in this plate and insert it on the sample holder. So we can measure using this true microphone technique and using this in situ measurements at the same time. So basically we model using our proposed model, here I call it Serrano model, so, but yeah, and then we compare with the analytical literature review models we study, and experimental results. So we got a fairly good agreement with the literature and the experimental data, and we could improve a little bit the reactance. Here is the reactance, the mass reactance, just taking out the cavity reactance. So we have just the reactance of the facing sheet, and this is the normalized resistance of this line, both on frequency domain. And this sample here has a porosity of 5.2, is the flanged one, this measurement with the flange. And the second one is the measurement using this sample holder. Okay, we consider that it's a very good result by now. And then on the second year, we use this rig here, which is composed by this fan that works in a reverse mode. We suck the air from the duct. This is a muffler, and then this tubulation here enters in a reverberant chamber, and then we have this extra muffler here, the diffuser, and this let's say nozzle that sucks the air from another chamber. And basically this is the test section, let's say, of our rig. So this is the team that worked there. My friends here, my slaves, I call them. No, I'm just kidding. This is Guilherme, this is André, and this is Baga. And this is the test section. Here you see that we put several microphones on the opposite side of the line in a squared tube. And okay, if we see the enter, this is the nozzle here. We have a pressure, let's say, we capture the pressure here at this point, the hydrodynamic difference. We can calculate the velocity, or let's say the speed of the flow in the tube. And these are 8 compressor drivers that give us some pressure levels up to 146 dB at the sample. The maximum we could get at that point using pure tone excitations. And this is a zoom here on this this section here. We have the line. There's a tiny microphone there we cannot see, but this in situ measurement we can measure at the same time using this technique. This one here, which is used in one of these let's say methods. It's called straightforward method. Basically it captures the decay of the sound pressure level along the line, and we have some other microphones away from the sample to use other techniques, the 2-port matrix and the mode matching technique. And basically we compare these 3 techniques I have just talked about with this in situ measurement, and we got a good agreement in certain, say, frequency range. But these impedance seduction techniques have some drawbacks, and especially at lower frequencies here. And the method, let's say, has some uncertainties all over the frequency range. And this is a zoom on the, let's say, a cross section of this design I need to do to insert this microphone. So we have a, let's say, a backing plate here with this part that we have the one microphone on the top and one microphone at the back of the cavity. Moving a little bit on the 3rd year now, we are studying how these numerical models work, and we have been seeing good job done by Zhang and Giordani. Basically, they use direct numerical simulations, DNS, and this is the difference that we can observe in the sound pressure level and how the flow here. This is the vorticity magnitude, and then you can see for lower sound pressure levels we can consider that the linear regime of excitation of this line. We have just the displacement on this neck of the Helmholtz resonator. it's located just in this region here, so we cannot see much of the vortex rings that are created for higher sound pressure levels. And this becomes the basic, let's say, and the most prominent dissipation mechanism in this kind of configuration. And to achieve this kind of regime here, it's very difficult. But we could model this in a simplified way using 2D models as well, and using these multi-physics models. So just quick expose here that we have the same configuration as the impedance tube. Okay, we have the position of 2 microphones to use this 2 microphone technique on the numerical model. We call this acoustic domain region. We consider the linear acoustics physics there. And then we have a boundary that has an interface with a laminar flow model using the Navier-Stokes equation. And then in this region we use the boundary condition like a no slip condition near the hole and slip condition on the sides of this tube. And basically the most difficult thing is how to match these 2 boundary layers, these 2 layers of physics. And this is the mesh. Just to take a look at one of the frequencies, the mesh is frequency dependent. So this is the refinement, minimum refinement that we need to capture all the boundary layer in this tiny hole, which has roughly 1 millimeter. And then the results so far show that this console, we are using this tool here, is the red results. We have a prediction model by Paul Murray, which is on the team here in blue. And the result is experimental results from NASA using this model, which is basically a slit liner configuration. And the TAM results is the DNS results. So we are quite satisfied with the results by now, but we are continuing to improve our model. And this is one result of our model so far. We can see that the velocity magnitude on the whole for the linear regime that I talked about for this geometry here have the, let's say, the highest magnitude just located near the hole. But when we move to higher sound pressure levels, I took the zoom a little bit bigger now. You can see that it's the same geometry of the hole, but this creates a jets. And then if we analyze the vorticity, we can see the vortex rings shedding in this configuration too. So the conclusions are that we proposed in the first year 1 degree of freedom model. So basically we could compare with the experimental results and the literature for high sound pressure levels and pure tone excitations using this normal incidence. And then on the second year we could extract some more results having grazing flow conditions that gives us broad experimental data or database now to work. And now we are improving our multi-physics model to finally have a very good visualization of the flow fields, the velocity fields, and try to, let's say, understand a little bit more physics in this phenomena and try to include this physics on a semi-empirical model and try to maybe improve our analytical models to use as a tool, say engineering tools in industry. So just to, the last graph here, just to observe that this is very important because these are the results, the solid lines for pure tones. We have the impedance, let's say resistance and these 2 resistance in 2 different configurations. The solid lines are pure tones only, and the dashed lines here are the effect of these multiple tones. So this is, let's say, an evidence that this multiple tone response changes dramatically the impedance of the liner. So that's what we want to see in the numerical results and try to reproduce in the equations later to model this problem properly. So thank you for listening. I would like to acknowledge the CNPq, my sponsor, Brazilian government. Jeremy, thank you for the support so far, and Homer Ray as well. Thank you very much for listening.